Greetings to all everyone. Today I'm excited to share with you the incredible world of digital logic components and their transformative role in shaping the future of self-driving cars. These intricate circuits form the backbone of autonomous vehicles, enabling them to perceive, process, and respond to their surroundings with remarkable precision. Firstly, let me introduce my team. Hello everyone, I'm Sami Hossain from CSC department and these are my fellow teammates Pronoy, Pranto, Rafsan, and Saiful. Today, we would like to talk about digital logic components powering the future of self-driving cars. Imagine a world where cars navigate seamlessly through complex environments, make informed decisions without human intervention, and offer a safer, more efficient, and more convenient transportation experience. This vision is becoming a reality thanks to the power of digital logic components. At the heart of self-driving cars lie intricate networks of electronic circuits that handle the immense amount of data processing required for real-time decision making and navigation. These circuits, composed of various digital logic components like encoders, decoders, multiplexers, adders, and gates, work in harmony to enable autonomous vehicles to navigate safely and effectively. Firstly, we have encoders. Encoders, the language translators of self-driving world, convert analog sensor signals into digital representations, allowing the central computer to interpret the data accurately. Decoders, on the other hand, perform the inverse operation, transforming digital data back into analog format and enabling the card to understand sensor information effectively. Multiplexers, the data flow ensure that the central computer receives only the most relevant data at any given moment, preventing it from being overwhelmed by or less important informations. Adders, the arithmetic wizards perform complex calculations such as determining distances to objects and calculating relative velocities, underpinning autonomous navigation and obstacle avoidance. Finally, gates, the logic architects from the building blocks of digital logic circuits performing simple operations like AND, OR, NOT, NAND, NOR, and XOR, laying the foundation for more complex logic designs. These digital logic components work in unison, enabling self-driving cars to perceive their surroundings through sensors, process the vast amount of data generated, and make informed decisions in real time. This intricate interplay of hardware and software is the driving force behind the self-driving revolution. As we move forward, digital logic will continue to play a pivotal role in shaping the future of autonomous vehicles with advancement in technologies. We can expect even more sophisticated features, enhanced safety measures, and broader adoption of self-driving cars, transforming the way we perceive and experience transportations. From here, I would like to invite my teammate Pranay to continue from here. Thank you, everyone.
Hello everyone, my name is Pranaypal. Today I will talk about why digital logic components are important for the future of self-driving cars. You might be wondering, is this technology truly future-proof? Okay, let's take some time to discuss this in detail. Digital logic components including encoders, decoders, multiplexers, adders and gates play a crucial role in the development and advancement of self-driving cars. These components are essential for enabling real-time data processing, accurate sensor interception, and intelligent decision making, which are fundamental requirements for autonomous vehicle to navigate safely and effectively. Well, in real-time data processing, the sheer volume of data generated by various sensors in a self-driving car demands efficient and reliable data processing capabilities. Digital logic components enable the system to process sensor data in real time, ensuring timely response to changing environments and potential hazards, like digital signal processors. Digital signal processors are specialized processors designed for real time signal processing applications. They excel at tasks such as filtering, noise reduction, and feature extraction. In self driving cars, digital signal processors are often used for processing sensor data from LiDAR, radar, and cameras. Then, graphics processing unit. Graphics processing units are highly parallel processors originally designed for graphics rendering. Their parallel architecture makes them well suited for handling the massive amounts of data generated by self-driving cars. Graphics processing units are commonly used for tasks such as object detection, scene understanding, and path planning. Then we talk about the accurate sensor interruption and microcontrollers. In accurate sensor interruption, digital logic components enable the system to decode sensors signals, convert analog measurements into digital representation, and extract critical information like distance, velocity, and object detection. On the other hand, self-driving emergency vehicle could provide rapid and reliable assistance in critical situations with enhanced safety measures and accident detection capabilities. Then, microcontrollers. Microcontrollers are small scale embedded computers that offer a balanced performance, power consumption, and cost. They are commonly used for low level control tasks such as actuating motor controls and managing communication protocols. In self driving cars, microcontrollers are often used for tasks such as steering control, braking control, and sensor data acquisition. Microcontrollers are made up of many digital logic components, but some of the most important ones include central processing unit, which is CPU, then memory, timers, analog to digital converters, digital to analog converters, and serial communication ports. Well, now we talk about intelligent decision making. Self driving cars with seatbelt detection and weather informed recommendations could transform ride sharing services. The sheer volume of data generated by various sensors in a self driving car demands efficient and reliable data processing capabilities, which is dependent on multiplexers. In essence, digital logic components are the backbone of self driving car technology, providing the computational power and decision making capabilities necessary for autonomous vehicle to operate safely and effectively. Thank you.
Hello everyone, I am Prantopal. In this presentation, I am talking about the circuit which we used in this project. Self-driving cars are like futuristic wonders, effortlessly crashing through complex surroundings and making smart decisions all their own. This incredible capability is achieved through a combination of advanced hardware and software, with a key player being digital logic. Let's dive deeper into the fascinating world of this circuit, understanding how they enable self-driving car to perceive, process, and respond with remarkable precision. Encoder, the language translator. Picture self-driving cars as having super senses, gathering information from sensors like LIDAR, radar, cameras, and ultrasonic sensor. Yet there's a challenge: these sensors speak in an analog language, and the car's brain, the central computer, only understands a digital language. Here's where encoder comes into play as a language translator. They convert the analog signal from sensor into a digital language through a process known as analog to digital conversion. This conversion is like turning sensor message into a digital code that the central computer can easily understand, ensuring accurate measurement of distance, velocity, and other vital parameters. Decoders, unrevealing the digital code. Once armed with digital sensor data, the central computer needs to interrupt and understand it for effective decision making. This is where decoders comes in. They perform the reverse function of encoders, converting the digital sensor data back into analog format through digital to analog conversion. This decoding process allows the central computer to make sense of data and build a comprehensive understanding of the vehicle surrounding. Multiplexer, data flow orchestrators. Imagine the constant flow of data from various sensors. It is like managing a symphony. Multiplexer act as conductor in this data orchestra, orchestrating the flow and ensuring that the central computer receives only the most relevant data at any given moment. Acting as intelligent choice, multiplexer select critical sensor data based on control signal. This selective data delivery prevents the central computer from being overwhelmed by redundant or less important information, allowing it to focus on most pertinent data for real-time decision making. adder, arithmetic wizard. Self-driving cars need to make smart decisions, and that involves complex calculation. Enter adders, the arithmetic workshops of digital logic. Adders perform the fundamental operation of addition, a cornerstone of many mathematical operations. They calculate distance to object, determine relevant velocities, and handle other critical computation essential for autonomous navigation and obstacle avoidance. Gate. At the core of digital logic, circuits are gates, the architect of logic. These gates perform simple operations like AND, OR, NOT, NAND, NOR, and XOR, forming the foundation for more complex logic design. Think of them as the decision makers with the car's brain. They control various aspects of self-driving cars, including decision-making, control signal, safety, measurement, constructed using transistor or other electronic components, gates which between voltage level representing logical states. And now, digital logic components are unsung heroes behind the scenes, forming the invisible backbone of self-driving car. They empower this vehicle to perceive, process, and respond to their surrounding with unparalleled precision. From encoding sensor data to performing complex calculation and orchestrating data flow, these digital components are driving force behind the self-driving revolution as technology advances. Digital logic will undoubtedly continue to play a pivotal role in shaping the future of autonomous vehicles, paving the way for a world where self-driving cars shamelessly integrate into our transport landscape. Thank you.
Hello everyone, I'm MM Rapsanjani Shorov from CSE department. As my teammate says, self-driving cars are revolutionizing the transportation industry, offering the promise of safer, more efficient, and more convenient journeys. At the heart of these autonomous vehicles lies a complex network of electronic circuits that handles the immense amount of data processing required for real-time decision-making and navigation. To ensure the seamless operation of self-driving cars, circuit design optimization plays a crucial role in maximizing performance, efficiency, and reliability. Power consumption, the driving force of optimization. Self-driving cars are powered by batteries, and their limited energy capacity necessitates careful power management. Circuit design optimization plays a crucial role in minimizing power consumption, thereby extending battery life and ensuring the vehicle's ability to operate for extended periods. This optimization involves selecting efficient circuit architectures, utilizing advanced semiconductor technologies, and employing techniques like clock gating and power gating to reduce power consumption during idle periods. Speed, the essence of real-time decision-making. Self-driving cars must process vast amount of sensor data and making critical decisions in real time to navigate complex environments and ensure the safety of passengers. Circuit design optimization for speed is therefore essential, enabling the system to respond swiftly to charging conditions and maintain control of the vehicle. This optimization involves employing high-performance logic circuits, employing parallel processing techniques, and optimizing data paths to minimize latency, area efficiency, striking a balance in limited space. Self-driving cars are designed to be compact and efficient, and their electronic components must occupy minimal space. Circuit design optimization for area efficiency is crucial to prevent the system from becoming bulky and cumbersome, reducing the vehicle's overall size and weight. This optimization involves employing compact logic circuits, optimizing the placement of components on the circuit board, and utilizing advanced packaging technique to minimize the physical footprint of the circularity. Techniques for circuit excellence. Several techniques are employed to achieve optimal circuit design for self-driving cars. Logic synthesis turn high-level descriptions into efficient gate networks aiming for small, fast, and power-hungry circuits. Technology selection. Choosing the right technology like CMOS, GaN for performance, power, and cost balance. Circuit layout. Arranging components for speed, efficiency, and reliability. CAD tools help navigate the complexity. Power management. Every watt counts. We use techniques like clock gating and power gating to shut down unused circuits, saving precious power for when it needs most. Low power design. We employ low power components, optimize data paths, and use efficient transistors to keep the energy meter in check. Thank you.
Thank you, Robson. From here, I'll be taking over. I am Saiful Islam. Now, here in the techniques for circuit excellence, here we also consider the parallel processing. With parallel processing, it will split complex tasks for faster processing using hardware or software, and it increases speed, but it adds complexity. After that, here comes the high performance packaging. With high performance packaging, it will reduce the sizes and improves heat dissipation of circuits using advanced techniques like flip chip and or stacked die packaging. After this, we come to the gates and cost calculation. And this is a crucial part where we will take consideration with some factors that will help us to get the mainly optimal output of the cost that we are going to use here. Now, for the cost calculation for the logic components, the following factors should be considered. First of all, that will become considered is the component cost, the individual cost of each component, including encoders, decoders, multiplexers, adders, and gates. Accurate cost estimates are essential for budgeting and for this project to work out. Now, if you come to circuit design complexity, the complexity of the circuit design, which affects the number of components required and their overall cost, simply is often a cost-saving strategy. After that, there we can take consideration the manufacturing cost. The manufacturing costs associated with producing these circuit boards and integrating the components, negotiation with the supplier can help to reduce the manufacturing cost. After that, a crucial part is the testing and the quality assurance. The cost of testing and verification procedure to ensure the reliability and performance of the digital logic component is investing a quality assurance can provide costly rework or failure. Now, if we come to the circuits, that how many circuits we'll be needing here and what circuits. In for our project, we'll be needing about three circuits. That is, I mean, three types of circuit. That is sensor interference circuit. We will be needing approximately 10 circuits. After that, we'll be needing data processing circuits, approximately 20 circuits, and then we'll be needing the actuator control circuits, approximately 5 circuits. So total we'll be needing approximately 35 circuits. Now, if we move on to gates, how much gates we'll be needing? We'll be using around 6 types of gate and we will be needing around 20,000 gates. And for the gates we will be using, we can use the AND gate, OR gate, NOR gate, NAND, NOR, and these gates will be needed to implement this project. After the gates, we take account for the encoder and decoder. The total number for the encoder and decoder are same because the data the encoder will encode, we will need the decoder to decode that. And for that, we'll be needing the LiDAR encoder and radar encoder, and this will calculate the distance for the various objects around the car. And after that, we'll be needing some ultrasonic sensor encoder, and then comes the seatbelt sensor encoder because we want to add that functionality to our car. After that, we will take account of for the multiplexer and adders, and here we will be using two multiplexers for the sensor data multiplexer and the control signal multiplexer to select the appropriate control signal to send to the actuators. And for the adders, we will be needing four adders. First, one adder for distance and one to measure velocity, and other two for calculation and planning the signal control generation. And after that, we come to the total cost here, cost calculation. And for that, one thing to be noted that to calculate the cost for all of these components, we have taken the Chinese market in consideration, because in our country we couldn't find the exact specific prices of these components and many other things, and we couldn't find many components available here. So we took the Chinese market in consideration because there is a wide variety and range of products there available, and also cheap in cost. And for all the encoder, decoder, multiplexer, adder, and gates, we will be needing approximately 9,300 Chinese yuan. And if we convert it into the USDT, we will be needing approximately 1,300 USD for the all the logic components, all the digital logic components, adder, multiplexer, and all the gates for them. And after that, there are some limitation in our project, because with if we could overcome this limitation, our project could have been much better. The limitations were the circuits that we have implemented here, they were very hard to simulate in Logisim for us, and so we couldn't show that in our project. And then comes the diagram, complex block diagram. The circuits diagram were also really complex, and components unavailability. In our country we didn't find some of the components. Then comes the lack of real life experiments. Here we mean by the testing and all the other things. If we can test our circuits and many other things, we can bring up some optimal outputs here. And then there comes the insufficient knowledge about some circuits, because here because our project, if we think about it in a large scale, our knowledge lacks here, because we have tried to make the project, think about the project in our limited knowledge. And by the time we will gain more knowledge, we can work on this project and we can make it more advanced. And then comes the conclusion, that the advanced self-driving car project exemplifies the transformative power of digital logic components in shaping the future of transportation by integrating multiple circuits effectively, designing optimized gates, and careful calculating costs. Now, from this, the engineers can create autonomous vehicle that offers more safer, more efficient, and more accessible mobility for all. As technology advances, the role of digital logic in future in vehicles and all the other sector will be much more sophisticated, and we will be very enhanced, and this will also provide much more sophisticated features with enhanced safety in many other sectors of the future technologies. Thank you.